Hello students, in this video we'll see an example of using the Laplace transform to solve an integral equation. Let's consider the integral equation y of t is the sine of t minus 2, the integral from 0 to t, y of s, the cosine of t minus s ds. If we look at this equation, even though there are no derivatives, I can still use the Laplace transform to solve, since this integral term over here is exactly y convolution cosine. And we know that if we take the Laplace transform of the convolution of two functions, I will simply multiply their Laplace transforms. So we'll solve this integral equation by taking the Laplace transform. Let's take the Laplace transform. If we do so, the left-hand side becomes y tilde of s is equal to the Laplace transform of sine, which we know is 1 over s squared plus 1, minus 2. And now I have y convolution cosine. That will transform to y tilde of s, the Laplace transform of y, times the Laplace transform of cosine, which is s over s squared plus 1. Now we have a linear equation for y tilde. We'll rearrange the equation. This implies that y tilde of s times the quantity 1 plus 2s over s squared plus 1 will be equal to 1 over s squared plus 1. Now we will simplify the left-hand side. The left-hand side is going to simplify to y tilde of s times the quantity s squared plus 1 plus 2s over s squared plus 1. And this will be equal to 1 over s squared plus 1. Taking the reciprocal of both sides, what we will do is we're going to multiply both sides of the equation by the quantity s squared plus 1 over s squared plus 2s plus 1. And if we do that, the left-hand side is going to simplify to just y tilde of s. And the right-hand side will simplify to 1 over s squared plus 2s plus 1. And then we'll have to find the inverse Laplace transform of this. We can notice, however, that this expression over here is a perfect square. So this tells me that y tilde of s is equal to 1 over s plus 1 quantity squared. And we can now recall that the Laplace transform of t is 1 over s squared. And the additional rule that e to the at f of t Laplace transforms to f tilde of s minus a. We can apply both these rules in conjunction to inverse Laplace transform this function. This function inverse Laplace transforms to, well, I'm going to have a shift of -1, and I'll have a t, so I'm going to have a t e to the negative t. And that's the solution of our integral equation. One thing to note is that since convolution is commutative, our equation is equivalent to the equation y of t equals sine of t minus 2, the integral from 0 to t of y of t minus s cosine of s ds. So this integral equation is an equivalent problem. So it wouldn't matter if I had the order of these functions flipped. The convolution procedure gives me exactly the same result. So we see that by using the Laplace transform, we're able to solve integral equations of this type. Thank you very much.